Hello again, everybody. Here we go on the next screencast lecture. Today's topic is life. Where does it come from? People have been wondering about the origin of life for pretty much forever, and people come up with all different kinds of ideas of where life came from. Back in the Middle Ages, a person observed that mice would often appear if you left a bag of grain laying around for several weeks. And you probably have noticed this too if you've ever left a plate of food in your room and you didn't clean up after yourselves. You might find ants or bugs around. Now
and fruit flies.
And fruit flies, speaking of which. Here's a recipe for mice that Dr. Jean-Baptiste von Helmont came up with back in the Middle Ages. He said if you took a dirty garment or a dirty shirt and you threw it together with a bunch of wheat and you left it sit around for about a month, you will be able to create mice. And sure enough, that probably would happen. Like I said, you probably get bugs or fruit flies or something around. And the idea that living things come from non-living things, this was known as what's called spontaneous generation. And to you and I, that might sound a little bit ridiculous, but it really isn't if you think about it. So again, if you take fruit and you leave it out in a trash can for a few weeks, especially on a hot summer's day, you're very likely going to find maggots. Those maggots are these nasty little larvae from flies. And, I mean, that's happened to me more than once. I'll open up my trash can and you see a whole bunch of maggots in there. It's disgusting.
What are maggots?
What are maggots? They're like baby flies. They're really gross. And earthworms. What about earthworms? So if you've ever been outside after a very, very strong rain, you may have noticed there are a whole lot of earthworms on the ground. So it might be reasonable to think that the rain produced the earthworms. Here's a fella. His name is Francesco Redi, and I like to talk about famous scientists and their famous experiments. Here's one experiment that is very, very well known, and it's often called simply Redi's experiment. People know what you're talking about. And like I said, people mentioned that they leave out meat. They would often find maggots on their meat. And this would have been a very common occurrence for people back in Redi's time because they wouldn't have had screens on their windows. You wouldn't have had a refrigerator, so you would have kept meat exposed. Like you would go to the market and you would find raw meat sitting there. The best way to store meat in those days was probably to keep it alive, like in a cow or a pig. So you have your live cow, it stays fresh. So Redi observed that these maggots would come on the meat, but he just really wasn't satisfied with the idea that the meat itself created the maggots. So his problem is to figure out where did the maggots come from? How did the maggots get on the meat? He had a hypothesis. He thought that the maggots might come from other living things, not from the meat itself. So what he did is he set up his experiment. This is Redi's famous experiment. The first thing he did is he got 3 jars, special glass jars that were all identical. And when you're doing an experiment, you want to try to keep things as similar as possible for all tests, except for the actual variable that you're trying to test. So after he placed the meat in each jar, he left one of the jars uncovered. So this jar he left uncovered. This jar he sealed tightly with a lid. And this jar he put what's called cheesecloth over it. It's like a mesh. It allows air in, and however, it is probably the best way to think about it is maybe like a screen that you'd have over your windows. He left the meat out for several days and observed what happened. The unsealed jar looked like this. The completely sealed jar looked like this. And the cheesecloth jar looked like this. So go ahead and look at these and draw your own conclusions. How did the maggots get onto the meat? Well, one of the things you see is that there are flies all around, and during Redi's time, that certainly wouldn't have been an unusual occurrence to have flies around your house. So that wasn't a shock. However, you notice that the one that's sealed tightly does not have flies around it. The one without a lid at all, flies could get in the jar. The one with the gauze covering it, the cheesecloth, could get near the jar but couldn't quite get in the jar. Here's a pictorial summary of his experiment. Again, take a look at this, and you can see all the flies and the nasty open jars down here, and the meat down here is starting to decay, and this one, the meat looks... So the correct conclusion is that the flies were able to get to the meat, they laid eggs, and those eggs would hatch and form the maggots. The maggots over here were on the cheesecloth because the flies could smell the meat. They thought the meat was nearby, so they laid the eggs nearby, thinking that the maggots would be able to get to the meat to feed. The sealed jars, the flies couldn't get to the meat. They couldn't really smell the meat, so they were not going to lay eggs in that area. Our next famous scientist and famous experiment is Lazzaro Spellenzani. And what he did, he took chicken broth, which is like chicken noodle soup, but without the noodles, without the chicken pieces, and he used a microscope to look at the soup, and he saw that there were a lot of microorganisms, really tiny critters, microbes living in the broth. He then boiled the broth, and then when he looked at the broth under a microscope again, he noticed that the microbes were gone. Where did the microbes go? Well, you may know that boiling will help to kill the germs, help kill the bacteria that's in the broth or water, things like that. And that's what happened. So he killed off the microbes by boiling it. But then he discovered that if he let the broth sit out for several more hours, and then he looked at the broth again under a microscope, that the little beasties, the little critters were back, that the bacteria was back in the broth and has recontaminated it. He thought that the contamination was caused by air, because he figured, hey, air can get in and out. That's what causes the contamination. So he wanted to test the idea that air causes contamination. How could he do this? Well, what he did is he kept air from getting into the flask. To do that, he put a stopper in it and then started heating it up, just like he did before. The broth was killed. The broth was killed. The microorganisms were killed in the broth. The microorganisms were killed in the broth. He left the open one sit. The microorganisms came back. He left the one that's sealed sit, and the microorganisms did not come back. So his conclusion makes total sense, is that the air actually caused the contamination. Here's a summary of what he did. In his experiment, he incorrectly concluded that air caused a contamination. Also in this experiment as shown, there's a major safety hazard. Can you spot it? Hopefully you did. You should not heat up a sealed flask. This is a sealed flask. If you heat this up, the pressure inside can get very great, and the flask can explode. Canned foods. The way canned foods are made is that you take the food item or the water or the liquid and you heat it up, and it kills off all the germs. Then you seal the can airtight, and the food stays fresh for a much, much longer period of time than if you didn't can it. In the early 1800s, Emperor Napoleon of France had a big army that he needed to feed, and he was having a hard time keeping fresh food for his army. So what he did is he came up with a contest and said, if anybody can come up with a way to preserve food, I'm going to give you a big money prize. And this guy actually did win that money prize. He came up with an idea of using bottles to heat up the food, and then he would seal it airtight, and the food would stay fresh for a much, much longer period of time. Good job, good thinking. And Louis Pasteur was another French guy. He came along later, and he used some of these ideas to help to preserve wine and milk. Louis Pasteur disagreed with Spellenzani's idea that air contaminated the broth. He didn't think it was the air that contaminated the broth because air is a non-living thing, and he thought that living things should only come from other living things, and air is not living. He actually thought that bacteria that lives on small particles of dust is what caused the contamination. The way he tested this is he came up with an idea of a swan neck flask. So what it is the flask is open, the neck has this really weird bend to it. So that way air could get in, so air can go in and up this tube, but if dust were to fall in it, the dust would stay down here and would not travel up the tube. So it would keep dust out of the flask, but allow air to get into the flask. Pretty clever. This flask opens straight up, so dust would be able to fall straight in and get into the broth. Dust falling down here would not be able to do so. He heated up both flasks, and the microorganisms were killed in both flasks, just like he thought. He left both flasks sit out, and the one with the open neck that went straight up where dust was allowed to get in got recontaminated, bacteria growth, versus the one with the swan neck flask, the dust did not get in, the bacteria did not start regrowing in the wine or the milk. So he discovered a way to purify and store wine and milk even for a much longer period of time than you would normally get. Here's a video clip of Pasteur's experiment. Let's check it out.
It was known that microbes are found in many places. Pasteur himself had found them on dust particles in air and in vats of soured alcohol. The problem was, no one knew for sure where these microbes came from. Many believed they were created by a special life force in the air, in a process they called spontaneous generation. Pasteur thought this was nonsense. Like some others before him, Pasteur believed that microbes could be carried by, but not created by the air. So Pasteur formulated a hypothesis, an educated guess that gives a possible answer to the problem. He hypothesized that a flask of broth would stay sterile as long as no airborne microbes could get in and use the nutrients in the broth to multiply. He then tested his hypothesis by conducting an experiment. Pasteur placed broth in special swan-necked flasks and heated them to force out all of the air. As the broth cooled, the air could get back in, but dust and microbes could not, because they became trapped in the swan-shaped neck. Pasteur observed that the broth in the flasks remained clear and therefore sterile. When he broke off the neck of the flask, allowing airborne microbes to get in, the broth became cloudy as the microbes grew within it. Pasteur concluded from these results that he should accept his hypothesis, rather than rejecting or modifying it.
In 1859, Louis Pasteur disproved spontaneous generation. The bacteria did not come from the air is non-living, but from the bacteria living on the dust floating around in the air. And you probably have heard, or if you haven't, take a look. The next time you look at a carton of milk, you'll see the word pasteurized milk. That's the process that Louis Pasteur came up with superheating the milk. That would kill the little beasties in the milk and help keep it from becoming spoiled and getting you sick. Here's a video clip showing you a modern milk factory and how milk is prepared for you.
Milk is an emulsion of fat globules suspended in water. If raw milk is left to stand, the fat will rise, forming a layer of cream on the surface. This was the only known method of producing cream until the second half of the 19th century, when the cream separator was invented. The homogenization produces a permanent emulsion of smaller globules, which are evenly distributed throughout the liquid. This is why homogenized milk tastes creamier than unhomogenized milk. The homogenized milk goes to the pasteurizer to be heated to a temperature that will destroy harmful bacteria, together with most of the bacteria that causes milk to spoil. This is achieved by heating the raw milk to a minimum of 72 degrees Celsius, holding it at that temperature for 15 seconds and cooling it back down to 2 degrees Celsius, designed to kill bacteria quickly and minimize the damage to the flavour and food value of the milk. The pasteurizer consists entirely of plate heat exchangers. The milk never comes into contact with steam or cooling water. Before pasteurization, milk needed for cream and skim milk goes to the separator, a modified high-speed centrifuge. It can be regulated to produce cream of varying fat concentrations. Cooling is the critical factor in processing milk ready for packaging. After homogenization and pasteurization, the milk is tested again to make sure that the 15-second burst of heat has killed the target group of bacteria and that the product has been cooled down properly to just below 2 degrees Celsius. Having passed all tests, the milk is pumped to the packaging area. After the cartons are filled, they move to the sealing section, where they're ink jetted with a use-by date. The ink jetting machine also keeps a record that enables the factory's quality control people to trace back any particular batch of milk.
So spontaneous generation is out. So now what? What can they come up with next? Well, you probably remember this from last year, at least I hope you do. Cell theory, and again, take a look at the Every Living Thing is Made Out of Cells video. That's going to be a good review for you to go over cell theory. Every living thing is made of cells. Cells are the basic building unit of life. All cells come from other cells. There you go. So that's the big one. All cells come from other cells. And that brings us to the term called biogenesis. Biogenesis, bio meaning life, genesis meaning beginning. This is the theory that living things come from only other living things, not from non-living things. So where did the first cell come from? That would be the obvious question most people ask if they get the chance. And I think that's a great question. So how are organic, these are living materials produced from inorganic, non-living materials? How are we going to get these living materials from? Scientists believe that the early atmosphere was made out of inorganic materials like ammonia, hydrogen, methane, water vapor. All these are non-living, not organic materials. There's a fellow named Miller. He did an experiment where he took chemicals, ran electricity through these chemicals, and he found that some amino acids, which living things use, were produced. So he did produce material that's used by living things from non-living things. Here's something that's very important to know, though. Miller's experiment did not create new life. He produced chemicals that are found in living things, but he did not create new life. Here's a video clip. This is a famous scientist known as Carl Sagan. The awards, the science awards that we give out here at MagSig are named after him, the Carl Sagan Award. He explains the Miller experiment.
Molecules of life arise.
In a laboratory at Cornell University, we mix together the gases and waters of the primitive Earth, supply some energy, and see if we can make the stuff of life. But what was the early atmosphere made of? Ordinary air? If we start with our present atmosphere, the experiment is a dismal failure. Instead of making proteins and nucleic acids, all we make is smog, a backward step. Why doesn't such an experiment work? Because the air of today contains molecular oxygen. But oxygen is made by plants. It's pretty obvious that there were no plants before the origin of life. We mustn't use oxygen in our experiments because there wasn't any oxygen in the early atmosphere. But 4 billion years ago, our atmosphere was full of hydrogen-rich gases, methane, ammonia, water vapor. These are the gases we should use. Taking great care to ensure the purity of these gases, my colleague, Bishankari, pumps them from their holding flasks. An experiment like this was first performed by Stanley Miller and Harold Urey in the 1950s. Starting gases are now introduced into a large reaction vessel. We could shine ultraviolet light on this mixture, simulating the early sun. But in this experiment, the gases will be sparked, as the primitive atmosphere was by early lightning. After only a few hours, the interior of the reaction vessel becomes streaked with a strange brown pigment, a rich collection of complex organic molecules, including the building blocks of the proteins and the nucleic acids. Under the right conditions, these building blocks assemble themselves into molecules resembling little proteins and little nucleic acids. These nucleic acids can even make identical copies of themselves. In this vessel are the note of the music of life, although not yet the music itself. No one so far has mixed together the gases and waters of the primitive Earth, and at the end of the experiment had something crawl out of the flask. There's still a great deal to be understood about the origin of life, including the origin of the genetic code. Incidentally, there's nothing in such experiments that's unique to the Earth. The gases we start with, the energy sources we use, are entirely common through the cosmos. Chemical reactions, something like these, must be responsible for the organic matter in interstellar space and the amino acids in the meteorites. Similar chemical reactions must have occurred on a billion other worlds in the Milky Way galaxy. Look how easy it is to make great globs of this stuff. The molecules of life fill the cosmos.
Well, that's all, folks. Hopefully you learned something. Make sure you finish your notes. See you next time. Toodles.
But turbo bills, you can for kids. Bye.
Sunburn.